We're good. Okay. Good evening, everyone, and a nice warm welcome to our annual Early Careers and Student Showcase. Great to see so many of you, and welcome everyone online as well. So we have 3 speakers tonight, so we will hot-foot it through it to make sure that all our speakers get the relevant time. Very quickly, we have the formality of our annual AGM. It is quick, unless anyone has any objections. A few announcements. I'm finishing my tenure, and so we have a new incoming chair of the Scottish Committee, and our incoming chair is Fiona McClay. Give us a big wave. Fiona, make yourself known. If you haven't spoken to Fiona, please do make yourself known, and we look forward to your period, Fiona. We also have a new committee member in Tara Henderson. That's Tara. Welcome to Tara, and again, any questions and engagement, please catch up with Tara in our catch-ups. Our outgoing student ambassador is Zane. I don't think I saw Zane yet tonight. A massive thank you to Zane from all of us on the committee. If he watches this back and if he manages to make it on time, he's been really helpful and really a nice engagement with the student community. So we will find a new student ambassador in due time. Very briefly, items for consideration. Any feedback, it's probably the easiest. If anyone, please speak to me or any members of the committee. And we've got the email address there, but we genuinely are always interested in your thoughts on how we run the events, the venues that we use, the topics that we discuss, anything else that might be missing that you want to see from the Scottish Committee and the Scottish Centre of types of events and what we can offer you and how we can all work together. So please, any comments just now, or indeed through the committee or the email address. So before I start, any comments on the very quick formality of the AGM? So we have one event left of this current programme, and we're going up to Aberdeen again for our away leg, as it were. And we've got Steve McFarland from SEPA talking to us around coastal flooding, which will be very interesting indeed. So if you can make it, then again, as always, we'll be hosting a hybrid setup. And for anyone that fancies a trip to Aberdeen or is in Aberdeen, please come and see us. As always, you're all very welcome, any of you that members and non-members alike, but as always, just to try and outline some benefits of membership, including our journals, access to events, discounts at meetings. We've got our annual conference coming up, and indeed the Early Careers Conference coming up in July, and access to support grants and so forth. So please do check out our website for all the details and the benefits of membership. So we have 3 speakers tonight. As I said, we're not speaking in this order, but we have Tim Barnyard from the University of Bath, who's going to talk to us about gravity waves and the release of inertial instability. We have Ruth Dunn from Newcastle University, who's going to talk to us about rain gauge data. And our first speaker, it's actually in reverse, and we have Damaris Tan talking around modelling the impact of open biomass burning on UK air quality. I think this might be close to my last slide. The usual health and safety, we've made ourselves known, but any assistance, please talk to one of the team. There's no planned fire drills, but there's various exits if required. So without further ado, it's always easier when someone else is doing it. Damaris, our first speaker, going to come up. That's perfect.
It's a green light, so.
Yeah, that's great. Once you find your slides, usual rules. Damaris is going to give us a talk, and I'll host a very short Q&A at the end. We'll keep the momentum up to get to our speakers. Great.
There we go.
Over to you, Damaris.
Thank you. Right, hopefully everyone online can see this and hear me okay. Hello everyone, my name is Damaris and I am a PhD student at the University of Edinburgh and also the UK Centre for Ecology and Hydrology. And I'll be starting off the evening talking about my work on modelling the impact of open biomass burning on UK air quality. And so here I am defining biomass burning as wildfires, prescribed fires, and agricultural fires. And these have many impacts on the environment, including on air quality, which is the one I am interested in. I am particularly interested in PM2.5 concentrations. So this is particulate matter with an aerodynamic diameter of less than 2.5 microns. And the WHO annual mean guideline value for this is 5 micrograms per meter cubed. And we care a lot about PM2.5 pollution due to its impact on human health. So just to put a number on this, in 2019, there were an estimated 4.2 million premature deaths globally associated with PM2.5 pollution. So my aims here were to test a novel globally nested setup of the EMET4UK model, and then to use this to investigate the impact of biomass burning on PM2.5 concentrations in the UK. So first of all, a little bit about the EMET4UK model and why we need a globally nested version of this. And so EMET4UK is the UK configuration of the Europe-wide EMET MSc West atmospheric chemistry transport model. So this is just a giant model of the troposphere with metrology from the WRF model. And I have been using anthropogenic emissions from the HTAP version 3 dataset and also the NAEI. And I have been including biomass burning emissions from the FIN version 2.5 dataset. So first of all, I need to explain a little bit about how we usually run EMET4UK. So this is what I'm going to call the standard configuration of the model. So this, I can get the pointer working. Yeah. So this is where we have an outer European domain, which I have in orange here. And we run this at reasonably coarse resolution of 27 kilometers. And then this provides the boundary conditions for the UK domain, which I have in blue, which we run at very fine resolution of 3 by 3 kilometers. And at the edges of this European domain, we have what I'm going to call prescribed boundary conditions, which is just a set of numerical values, which we use as a proxy for transboundary pollution coming in from outside this European domain. And I should also say EU in this presentation stands for European Domain, not European Union. And BC stands for Boundary Conditions, not Black Carbon. But anyway, this sort of standard setup of the model works pretty well, especially when focusing on emissions within the European domain. The problem here is that I am focusing on biomass burning emissions, and most biomass burning occurs outside that European domain. And so just to illustrate this a little bit, on the right, I have plotted annual PM2.5 emissions from biomass burning from 2012 to 2023. And I have the UK contribution in blue, the European domain contribution in orange, and the remaining contribution in green. And as you can see, the vast majority of biomass burning does occur outside this European domain. And this wouldn't be accurately represented in this standard configuration of the model. And this is where we sort of need this globally nested approach. So what I mean by this is, instead of having these prescribed boundary conditions, I have introduced an additional model run. And this is over the entire global domain, which I have in green. And we run this at fairly coarse resolution of about 1 degree. And this then provides the boundary conditions for the European domain, which is again in orange. And as before, this provides the boundary conditions for the UK domain in blue. And I have done some model evaluation comparing model results to measurements across the UK. And I found that overall, the model does do well to represent inorganic and organic aerosols. Although overall it does overestimate compared to measurements. But we think this is due to overestimation in sea salt, which wouldn't really affect the results that I'm presenting here today. So with this globally nested version of the model, I simulated the year of 2019. I do realize this is just 1 year. I have done some work on trying to compare 2019 to other years, which I don't have time to get into right now. But the main point is that 2019 is a fairly average year when it comes to Northern Hemispheric biomass burning emissions. So if we see something happening in 2019, then we're likely to see this in other years as well. So for 2019, I did 2 main model runs. I did a base model run with all emissions switched on, and then I did a no biomass burning model run with the biomass burning emissions switched off. And then if I subtract the 2, then this should give me an idea of the impact that biomass burning has. And so moving on to my results. On the left, I have plotted the 2019 UK annual mean PM2.5 concentration that is conditional on biomass burning. And calculated across the UK, this gives an annual mean concentration of 0.99 micrograms per meter cubed. And sort of in the grand scheme of things, this isn't such a big number, but it is about 10% of the 2019 UK total mean PM2.5 concentration, and it's about 20% of the WHO annual mean guideline value. So if the UK does want to move closer towards this WHO guideline value, then I do think this is something that needs to be considered. I then went on to analyze this PM2.5 concentration in a bit further detail. So I was interested to see how much of this is associated with biomass burning within the different model domains. So I have this pie chart here, and again, I have the UK domain contribution in blue, the European domain contribution in orange, and then the remaining contribution in green. And as you can see, the majority of this PM2.5 concentration is associated with biomass burning outside the European domain. So this is about 73%. And I don't really think this comes as a surprise, given that most biomass burning is located outside the European domain. But it does sort of provide further justification for my use of this globally nested version of the model. I then took a look at the chemical composition of this PM2.5 concentration that is conditional on biomass burning. And I have another pie chart. So I have the primary organic matter component in the light green, the black carbon component in black, and then the remaining primary component in gray. And then I have nitrate, ammonium, and sulfate in blue, yellow, red, and then finally the secondary organic component in the dark green. So we can see that the majority, so 58% of this PM2.5 concentration is due to secondary aerosol formation. Most of this is the secondary organic matter in the dark green. But we do have quite a large contribution of secondary inorganic aerosol formation, most of which is the ammonium nitrate. And there is quite an interesting story behind that, which I also don't have time to go into now, but I do have a paper on that if anyone is interested. Yeah, so finally, I was also interested to see what the contribution of biomass burning in different regions across the globe would be to this annual mean concentration that I calculated. So I split the world into 8 different regions with 8 different colors, and I did a series of perturbation experiments to try and see how much these different regions influence this concentration in the UK. So I've added the percentage contribution onto this figure on the right, and we can see that most of this PM2.5 concentration is associated with biomass burning in the Northern Hemisphere, specifically Russia with 43%, and also Europe, Asia, and also Canada and Alaska. It should also be noted that 2019 was quite a low biomass burning year in Canada, so we do expect there to be a larger contribution, especially in more recent years. Yeah, and I should also say that the exact numerical results I have been quoting are very sensitive to many different factors. So for example, the meteorology and the anthropogenic emissions that I used, and of course, the biomass burning data set that I used. But I have done a number of sensitivity experiments, and these do indicate that while the numerical values change, the overall messages do remain the same. So just to finish off with some conclusions, so here I tested a novel globally nested setup of the EMET4UK model, and compared to measurements, this did do quite well to represent inorganic and organic aerosols, although it did overestimate compared to measurements, which we think is due to an overestimation in sea salt. I then went on to use this globally nested version of the model to simulate the impact of biomass burning on PM2.5 concentrations within the UK for 2019, which is a fairly average biomass burning year in the Northern Hemisphere. And I calculated a 0.99 microgram per meter cubed annual mean PM2.5 concentration over the UK, which is conditional on biomass burning. And about 73% of this was associated with biomass burning outside the European domain, which, while not surprising, did justify my use of the globally nested version of the model. And about 58% of this PM2.5 concentration was due to secondary aerosol formation, mostly organic matter and ammonium nitrate. And finally, most of this PM2.5 concentration is associated with biomass burning in the Northern Hemisphere, specifically Russia, Europe, and Asia, and also in other years, Canada as well. And finally, all these exact values depend on things like the meteorology I used, the anthropogenic emissions I used, and also the biomass burning emissions that I chose to use, and probably many other factors as well. So with that, thank you very much for listening. If you're interested, I do have a paper on this as well, which just got accepted in time for this meeting. So if you want to check that out, please do. And I'll also try and answer any questions that you have in person or online.
Thanks, Maurice. I'll take a very quick question to start with, just out of interest. Really interesting stuff. And I saw the variation across the UK in the image that you kept referring to. Out of interest, any comments around that? It was quite a marked variation, for example, between Scotland and other parts of the UK.
I think, so we were talking about, let me get it's right at the start.
It's even there, I guess.
Yeah. Oh, I'll get the big one up. Here we go. So we see quite an interesting sort of gradient going from, you can never do this under pressure, southeast to northwest. So I think there's several factors contributing to this. First of all, just meteorological factors. I'm not a meteorologist, but I do believe that we have, particularly in the springtime, we have a lot of easterly winds bringing pollution from Europe and further away. So that does contribute to this gradient, especially as the springtime is actually a peak time for these biomass burning related emissions, and also other types of emissions. And the second factor that I've been able to identify sort of explains the pattern that's superimposed onto this figure. I don't know how visible it is on the screen, but there's also, this is to do with the ammonium nitrate, the unexpected amount of ammonium nitrate that I sort of alluded to. So basically, that's related to other types of pollution, especially NOx and ammonia emissions. And these just happen to occur a lot in the southeast of the UK. So that's sort of the other contributing factor.
Thank you. Any questions?
Very nice talk, thank you. In the last few years, there have been some huge forest fires in North America and Canada especially, with the daily papers talking about PM raised in Europe simply because of Canada. So my question is, how typical is 2019 relative to recent years?
You mean in terms of where the biomass funding is located, or in terms of just absolute magnitude?
Absolute magnitude.
Okay, I do actually have a slide about this, which I'm very keen to show you. So this is what I alluded to when I was talking about comparing 2019 to other years. Yeah, so I think it would take quite a long time to try and explain this entire figure, but if you look at the bottom figure, and this is sort of my attempt to compare 2019, which is this bar here, to other years. So I've got 2012 to 2023. So to answer your question about how different it is from other years, just sort of eyeballing that, it's fairly average in sort of absolute magnitude. Looks like we have quite a large contribution from Russia, so that's the red one, and quite a small contribution from Canada and Alaska, which is the light blue one, compared to, for example, 2023, where that's quite a large year, and I expect 2024 would be similarly large, even though I don't have any data for that. So yeah, not sure how much more I can take from that. Yeah, anyway, thanks for the question.
Thank you. Perfectly timed talk as well, Doris. Excellent. Okay, we'll move on to Ruth, if that's okay. Thank you again, Doris.
Thank you.
Okay. So,
I think so.
over to you.
Circle. Oh, okay, great. Have I done something?
We are here, are we not? Swap this.
Oh.
Yeah, duplicate. Okay, thank you.
Thank you. Hello, everyone. I'm Ruth Dunn, a PhD student at Newcastle University, where I'm supervised by Hayley Fowler, Amy Green, and also Liz Lewis, who's based at the University of Manchester. Today, I'll be talking about quantifying the underestimation of rainfall by rain gauge networks, and focusing on the first couple of years of my PhD work. Okay, so just a quick presentation overview. So firstly, I'll just do a brief summary of the importance of accurate rain gauge data, then start discussing the limitations of this data, and focusing in on undercatch, which is the main focus of my PhD work. I'll talk about the shortcomings of existing undercatch correction methodologies, then the undercatch experiment, which is the fieldwork I'm doing as part of my PhD, and ending with some brief conclusions. Okay, so just very briefly, really, the importance of accurate rain gauge data. So sometimes rain gauges are thought of as sort of old technology, not really relevant anymore, but we still use them a lot. So from flood warning and mitigating systems right through to crop management, especially when we're moving to more automated systems with sprinklers and large scale crops. And then also as a way of validating, calibrating remote data or non-catching type sensors. And then in terms of inputs for hydrological models and maybe climate studies and water source evaluation. So it's a really important source of data that is used in many, many different applications. So one of the key limitations of rain gauge data is its spatial. Obviously, it's a point measurement, so it really struggles, well, it fails essentially to capture that spatial variation of rainfall. So when using rain gauge data, it's important to acknowledge that. And unless a network is very carefully considered and thought out in terms of the placement of gauges and the number of gauges needed, it can be very limited, that information you can gain from a single gauge. This is further complicated by the different designs of rain gauges we use. So different gauges will have different levels of accuracies and different issues associated with them. And then this is further compounded when we look at merging different data sets, so you can have different types of gauges in different locations, especially we're looking at multiple countries and regions and combining those to create one single data set. So yeah, it's very important to think about these things when using this data. However, the part that I'm really interested in is the issues at a local level. So looking at those inaccuracies at one specific gauge in isolation. And the errors at this local level can broadly be divided into two different categories. So you have undercatch, and that's essentially the difference between the amount of rain falling from the sky and the amount that is physically caught by that gauge. And then you have the counting errors, so the errors that are due to the actual mechanisms working within that gauge. So even when it's caught the rain, you can still get errors coming in because of the limitations of that mechanism. And this is focusing specifically on tipping bucket rain gauges. As these are the type most commonly used in the UK and what I'm focusing in on my PhD. And then the image on the, sorry, your right, I think, on the side of the screen, it's just trying to summarize the complexities involved when we think of these errors, because it can be very simple to say a catch-in error, but actually that's not a static issue. It's very much changes depending on the environment and the conditions around it. So in windy conditions, you get much higher levels of undercatch. So those exposed gauges, maybe sited at a slightly higher level, are much more prone to these issues. And that can cause great variation in the degree of undercatch experienced by gauges. Even these really fancily designed aerodynamic gauges are susceptible to it. And then it also goes into the installation, so how carefully that gauge was installed, and then maintenance monitoring checking. That's a really important issue with gauges. And that can affect the counting errors and give you some very strange results. So data cleaning and quality control becomes very important with those sort of errors. So undercatch reduction. So the first way to combat undercatch essentially is the gauges themselves have evolved over time. And you can see how that shape of the gauge has changed to try and reduce those wind effects with that more old school style, the cylindrical gauge at one side of the screen, moving across to that modern, almost sort of hourglass shape at the other side. So this also means if you're using a data set that spans multiple decades, you need to think how the gauges have changed within that data set and what impact that has on any summaries and conclusions you take from that data. And then also gauge installation practices and the use of supporting equipment. So this really highlights the importance of good metadata when we're using gauge data and understanding exactly how that gauge was installed, because this has a huge impact again on undercatch extent. And in some countries, they'll use windshields as a standard practice, and in other countries they won't. So yeah, it's something that can be really challenging to unpack when using these data. And then I've just got an example of a pit gauge, which is often used as the gold standard gauge, but can be very expensive to install. But that is generally considered to give you that best result in terms of windy conditions. But even then, they're not perfect necessarily all the time. So if we don't look at improving the equipment itself, how else can we solve the issue of undercatch? And a few different undercatch correction methodologies have been developed. And in my PhD, I'm trying to look at developing one specifically for a UK context and with the gauges that are used in the UK, both historically and presently. So first, considering the limitations of these existing undercatch correction methodologies. So frequently they have poor transversibility because they're very gauge and or site specific. So they've been developed for different regions, basically by different countries in the past. And you can't just pick up their correction factor and then apply it to a British-based network, essentially. Maybe they've got different gauge types, they have different challenges. Quite a few of them are based on quite outdated data sets now. Gauge design has moved on, or a very limited in volume of data. So that can make it less trustworthy. Another big issue is metadata gaps. So quite a lot of these correction methodologies require really detailed information about the sighting, the installation of the gauge, and the exposure. And quite often these records aren't available to us. And then on the other end of the spectrum, you can have oversimplified models. So sometimes you can have just a standard factor like that you multiply your data by for a month. And obviously within that month, there can be a huge variation in terms of winds and different factors that isn't captured if you just have one standard factor that you apply to that whole month's worth of data. And finally, the really intensive need for secondary sources of data. So quite often they'll require wind speed at gauge level or temperature information, and then drop size distribution data potentially sourced from a distrometer. Most of the British sites, we don't have all these additional data sets available. We just have the gauge or maybe 2 gauges installed. So that can be very limiting if you're trying to apply that to a UK context. So the main factors that affect undercatch extent in a UK context can be broken down essentially to 3 components. So that first one is that drop size distribution. So those different sizes of drops, whether it's a very fine rain or you've got large heavy drops. Typically a finer mist experiences worse undercatch, but then when you get the really big drops, maybe you get greater splash out and factors such as that. Intensity can also be a consideration. So very light rain can experience significant undercatch, and then typically very heavy rain also. So frustratingly, it's sort of the 2 ends of the spectrum that typically are most interesting can have the worst reliability in results. And then finally, the other factor I'm considering in my research is wind. And this is a really big component in the UK, very variable and important to consider when looking to improve any rainfall records or the reliability of that data. So the experiment that I've been working on is developing a rainfall simulator, which will allow me to control the droplet size by changing the nozzle setup on the end of that simulator. I can change the intensity of the rainfall by changing the pumping pressure. And then this can be taken out and used in the field to assess undercatch in different conditions. So this is the simulator being set up in a controlled environment, so where wind isn't a factor, and just looking at that basic setup. And I've been trying a wide variety of different nozzles. So to create that really fine misting rain, I've been using industrial nozzles that are typically used for sort of spray painting cars or cooling. And they've been developed to have a very fine mist and create a uniform cone of spray. So you shouldn't get an uneven distribution within that cone. I've also tried your classic sort of garden level nozzle, which is a fraction of the price. But as that photo sort of suggests, there's a reason why it's so much cheaper. And then we've tried really large shower heads to get that heavy intensity rain to see just how those would work. And then also a wide variety of different drip nozzles in different configurations. And from the preliminary results, essentially the garden level sprays have been discounted just because the quality of the distribution of that spray is not adequate. You get very much clumping and it didn't give very realistic rainfall simulation. And then the shower head was discounted because it basically requires too greater intensity of rainfall. Below a certain pressure, the shower head stops functioning properly and it becomes an unstable setup. So that was thrown out. So the misting nozzles and the drip fade nozzles seem to be the best setup. So the supporting equipment to check how well the rainfall simulator is operating. There's a distrometer that we're using to measure the speed and size of these droplets. And then this will be compared to the distrometer data for the UK and see how much it reflects naturally occurring rainfall, how realistic it is, and the different types of rainfall we're managing to recreate. There's a distribution grid that we're using to check how evenly spread that rainfall is over the area that it's falling. And then finally, we'll be putting rain gauges in there once we know exactly the type of rain that we're creating, the spread of that rain over that area, so we know exactly what's falling on that gauge, and we can compare what we know is falling on it to what it's actually measuring. So yes, this is just an example of the distrometer in use. And at this point, we had what they call a randomizer grid. So it's basically a mesh that we put the spray through to try and create a bit more random nature in those droplet sizes. And also with the misting nozzle, actually the spray comes out in slightly angled trajectories, and by hitting the mesh, it stops it being so angled, but it does introduce these larger droplets as well. So we're just really looking at all the different ways we could try and create different types of synthetic rain, and then seeing how that is most realistic in terms of what you actually see in reality. And then these are just some of the early results from those distrometers. So this is for that fine misting nozzle, and you can see it really is just generating those smaller nozzles. That's the droplet diameter along the bottom of the graph, and the speed is up the side. So you're getting those very small nozzles and not many larger drops at all. And then this is the shower head that was discounted, but just to illustrate the sort of the different types of drops that these two setups are creating, you can see the wide spread of droplet sizes that has been created by that. So we can effectively create different droplet sizes. It's just trying to make these setups as realistic as possible. So that brings me on to my next steps. So I'm currently trying different setups and configurations and really trying to get the most realistic rainfall simulator that I can. I will then use this in controlled environments without any wind, where I'm just looking at controlling that droplet size and that intensity on the different rain gauges and seeing what happens. And then ultimately take it out into the field, where I'll have a weather sensor and we'll record the wind speed and the other variables and see how that changes our results, and hopefully get a better understanding of the different factors that contribute to undercatch in different locations and how significant they are. The aim of doing this is to develop an undercatch correction methodology that can be applied to a UK-based data set. And finally, using this and applying it to a data set and seeing the impact of it. I am hoping to do this in my PhD, but I am rapidly running out of time, so we'll see if I get to that final step, but hopefully. So yeah, just in conclusion, really, rain gauge data is essential, but it is error prone, and we need to be aware of those errors when we use it. Existing undercatch correction factors are inadequate, particularly in a UK context. So there's definitely a need to develop a new one. And we need to think about the limitations of rain gauges when using that data. That's just a really important thing to think about. So thank you very much for listening. Just like to acknowledge my funders. So the first sort of chunk of this talk is discussing a lot more detail in a paper I had in Weather. So you can look up there, or feel free to reach out to me or ask me a question here. Yeah, thank you very much.
Thank you, Ruth. Another great talk, and bang on time as well. So I know we've got a couple of subject experts in the audience potentially, so I'll bypass my question if anyone has a question. Ruth?
Yeah, really interesting. But the one thing that you never actually mentioned was freezing or snow.
Yeah.
Now, we do get obviously heated rain gauges, but do we know what impact they're actually having? And have you looked at?
Yeah. So because I sort of be using the rainfall simulator as the center of my sort of PhD, and I'm not able to simulate snow, although people have suggested that we can do it on ski slopes, so why not try? I've not sort of unpacked that at all. I know that undercatch errors are much larger with snow generally, but I don't know the benefits of a heated gauge versus a non-heated gauge, and the different instruments. I know that there's such things as snow pillows, I think, and sort of alternatives you can use to measure snowfall. But I would be reaching if I was to give you sort of any opinions on those things, I'm afraid.
Yeah, thank you.
Another question at the back as well. Come on.
Great talk. Thanks very much, Ruth. Andrew Black from Dundee University. I spend a lot of my time, whenever I can, really out in the fields, messing with rain gauges or playing with the data from afterwards. I mean, just on the snow side, fascinating topic. I've had one heated rain gauge. It's 900 meters above sea level, and been surprised to see melt occurring in conditions when really it shouldn't have been occurring. There's a whole separate discussion there. But for Ruth, just one thing, maybe a little bit closer to home. I'm involved with the UKRI Floods and Droughts Research Infrastructure Program at the moment, and right now we're involved in our catchment monitoring design. What gauges should we have where for measuring precipitation? I think there's lots of discussion to be had, and I'd be super to have a chat with you about some of this. But the particular thing, I just wondered whether you have any knowledge or thoughts about the effects of fencing around rain gauges, which sometimes are a necessity in order to keep livestock away. I've had some thoughts about what's going on at some of my sites, and I wish I'd managed to negotiate for more field.
Yeah, I guess the big issue with these is, again, sort of you alluded to there, was space. So ideally, you'd have that fencing set well back from your gauge because you don't want that rainfall shadow influencing your gauge operation. But it's very difficult with these things because I think if you ended up with your ideal setup, you'd have sort of a pit gauge everywhere with a secondary gauge for backup, you know, so you have that quality control built in straight away. But yeah, it's definitely needs, I think, more consideration than it obviously often gets given when you're setting up your site. Yeah, so I think it's 3 times the height setback is a general rule of thumb when you have these sort of, to avoid that risk of a rainfall shadow. I guess a fence is complicated in that although the post is solid, then you get potentially the wire between it, and is the wire an issue? Yeah, it's. Oh, I see. Yeah, yeah. Yes, yeah, definitely, definitely. Yeah, there's just so many things I have to say with this project. I was talking to someone earlier and I said it felt like a quite contained problem when I started. And as I've unpicked it, it just gradually has unraveled more and more and more. And sort of the complexity and just involved. I think it's definitely more than a PhD sort of scale of work. But
some members here visited this gauge of the power reservoir, and Newcastle University had used it. It would be at your disposal if you have an interest there. I better stop there.
Thank you.
Thank you very much for the questions indeed. We've got one online, if you don't mind, a third question.
Here we've got a question from David Stevenson online, who's asking, do you have a feel for how large percentage typical undercatches are? And I actually had a question myself, which is about plant material getting into rain gauges and clogging them up, if that's something that's taken into account as well.
So I think that first question, I would be very cautious to say a typical percentage in that it varies so much. So in very still, calm conditions, it could just be 1 or 2%, like very small with these new high-end rain gauges. However, in windy conditions, so exposed, especially up on hilltops, you can look at sort of extremes of like 50% even, or potentially higher. So I think it'd be very sort of naive of me to give you a typical extent of undercatch. I don't know if that sounds a bit like a cop-out, but yeah, I think you really need to just think of the conditions associated with your gauge. And then in those conditions, sort of what are the ranges you're looking at? And generally, a more sheltered, lower level site where you have limited obstructions around it and it's been well installed, it's much sort of lower levels. And then those higher up exposed sites, you're looking, especially on windy days. Unfortunately, that can be obviously when you get the very heavy rainfalls, a much higher level. And in terms of debris in gauges, yes, so that's a really big issue. And basically you sort of rely on quality control. So often you use near like other gauges that are nearby, and you're looking to see, is this gauge not recording any rainfall for a long period of time when other gauges have recorded rainfall on sort of odd trends? And that can be your best bet, but depending on how close those neighboring gauges are, that can be quite limiting. It's definitely an issue if you have grass cuttings and things around it, or you can sometimes in city locations even get people dropping stuff in your gauge and things. So yeah, it's definitely an issue. Yeah.
Thank you very much indeed.
Thank you.
Yeah. So welcome, Tim, our final speaker. So just got something completely different again. We've got a real good range of, so it's great.
Yeah, very different.
I'll let you get yourself settled.
Make sure it's pointed the right way. Be this way. hear me, right?
Hopefully, it should just be a case of bringing it up.
Let me know if you can't hear me.
Do you still need us to swatch? Yeah, so it was just.
Yeah.
Okay. Over to you, Tim.
Okay, thank you. Okay, hi, I'm Tim Banyard and I'm a postdoc, actually at the University of Bath at the moment. This is some of my work from my previous postdoc at the University of Manchester, where I was studying under David Schultz. So I'd like to thank him and all the co-authors on this slide. The title is maybe slightly different to in your program, but it's essentially the same topic. And I'm really looking at clear air turbulence and trying to understand the role of gravity waves and regions of inertial instability in the production of clear air turbulence. That was a very short presentation. Again. I see what's happened. I started on the final slide. Okay, is that still set up for Zoom? There we go. That would have been very short. So first of all, a big question to ask at the start is, what is clear air turbulence? Many of you will have been on flights and you almost certainly have experienced turbulence of some kind. And often you will experience convective turbulence. That's quite simple to understand. If you have deep convection, lots of thunderstorms, planes flying through clouds, you get more turbulence. But some of the turbulence that's more tricky to avoid if you're a pilot is clear air turbulence, which of course you can't see. And clear air turbulence, of course, poses a significant challenge in aviation. It causes numerous aircraft incidents each year. Of course, the obvious things like structural damage, passenger injuries, and unexpected costs. So this is a really important topic to explore. And clear air turbulence is caused by a number of different things, and I'm going to be exploring some of those today. And listed there, the three main ones are shear instabilities, inertial instabilities, and gravity waves. And I'll explain what each of those are in turn. But in case you weren't convinced already, a paper actually from 2013, a while ago now, looked at the future impacts of climate change on turbulence. And what we see from that paper is that with a doubling of CO2, we see in a climate model at least, a projected increase in turbulence, in this case across the North Atlantic. And so this is an area where, of course, we see incidents of turbulence right now, but we might see more of those in the future as well. And as part of this paper, we see that the jet stream is projected to strengthen. And as a result of that, we encounter gravity waves at the edge of that jet stream where wind shear is the highest, and that is one of the contributing factors to more turbulence. But let's look at those three different mechanisms that I described. And the first of these is looking at wind shear. So that's where you have a change in the wind speed or direction, particularly as you increase in height. And if you look at the sort of the bottom panel here, this is looking kind of top-down view where you have just kind of in some fluids, a region of very fast-flowing fluids marked by a boundary with some slow-moving fluid. And very quickly, we see the development of Kelvin-Helmholtz instability. And a little bit of time later, that produces lots of turbulence as that instability decays away. So here we have the Richardson number, which is essentially the stratification on the top. It's kind of a ratio with the wind shear on the bottom. Where you have really high wind shear, the Richardson number is quite low. And there you have higher incidence of turbulence. The second process that I mentioned is inertial instability. And the best way to understand this, I think, is the analogy with convective instability. So if you imagine a kind of a parcel of air at the ground, if you were to lift that parcel of air upwards in a convectively stable atmosphere, that parcel of air will just sink back down. And if you have convective instability, that parcel of air will escape away upwards and you get lots of convection. And now if you think about the same parcel of air, but you move it laterally, so maybe towards the pole, so changing in latitude, the Coriolis effect, the Coriolis force will change. And if you have inertial stability, that parcel of air will just move back to where it came from. If you have inertial instability, it will race away exponentially, and then it has to decay at some point. So in this diagram here, along the x-axis, we have horizontal distance. On the left, kind of close to the equator, on the right, close to the pole. And you have altitude on the y-axis, and in color is the wind speed. So what you're looking at there is just the core of the jet stream. And on the equatorward side of the jet stream, you can see there's this kind of hatched region where we have inertial instability, where there's really, really high wind shear, and often you have what's called anticyclonic curvature, where the winds are turning around an area of high pressure cyclonically, so in a clockwise direction, and you have inertial instability in that region. The crucial thing is that this is from an idealized model simulation. And so we see enhanced clear air turbulence indices where this occurs in the idealized simulations, and I want to look at real simulations. But thirdly, the third mechanism I mentioned are gravity waves. And in this particular figure here, you can see, again, the Richardson number is plotted, these kind of wave phase fronts. And what happens is that, much like waves approaching the beach, as the gravity waves reach the beach, they will break and you get turbulence. As the gravity waves in the atmosphere propagate upwards, they also reach a point where they break. Often there is this kind of additional stretching of the atmosphere. The region becomes unstable and you get breaking and a deposition of energy momentum, similar to on the beach. So this is the sort of third mechanism. But as you may kind of have guessed as I was discussing those different mechanisms, they're all interrelated, and often it's a combination of 2 or 3 of these working together at once. And so really trying to decompose the cause of this clear air turbulence generation into these 3 mechanisms is quite a challenge. And in that idealized model simulation that I mentioned from this paper by Thompson and Schultz, we can see that where you impose, artificially, of course, a region of inertial instability in the atmosphere, about 72 hours later, we see the emission of gravity waves. And what the gravity waves are doing is essentially the same job as a thunderstorm would do at getting rid of the convective instability. It's dissipating the inertial instability by propagating the energy away to a different region. And you can see in the right-hand figures here, this is kind of a time series where you impose that inertial instability above and below it. You get gravity waves propagating upwards and downwards. But this is an idealized simulation. So do we see the same sort of thing in real life, in a real simulation? And also do we see it in observations as well? So what we want to do is we want to look at a classic case when we expect to see a lot of inertial instability. And in this example here from late September 2016, we have a strengthening anticyclonic ridge, strong warm air advection ahead of a deepening surface low, which comes in just in the left at the end. And as I said, regions of high anticyclonic curvature are known to be strong candidates for the occurrence of inertial instability and also clear air turbulence. So this should be a really good case to look at. And indeed, we look at observations. This is from the Aberystwyth MST radar site in the top left. And this, in this figure here, we can see a potential inertia gravity wave signature, which appears in association with negative potential vorticity, which I'll touch on in a minute. You can see that in the bottom left panel. And my simulation using WRF shows good agreement just at first order with the radar. And so this appears to be a good case to look at. Can Thomson-Schultz's ideal case connection between this release of inertial instability and gravity waves be replicated for a real case? So for my simulations, I have 2 domains. I have an outer domain, which includes the Northeast Atlantic, also includes the UK at 5 kilometers. And I also have an inner domain over the UK at 1 kilometer resolution with 150 levels for both. And crucially, gravity waves are, of course, caused by thunderstorms, kind of going upwards in the atmosphere. They're caused by potentially inertial instability. We see gravity waves at the edge of jet streams. But those are all non-orographic sources of gravity waves. Often the most obvious source of gravity waves are orographic in nature, mountains. And so if we are looking at gravity waves in our simulations, we want to make sure we're not just looking at mountain waves. So I've run simulations with orography turned on and orography turned off to basically try to take out the orographic waves. So looking at this simulation initially, we can see this kind of region, this anticyclone here. Just on the northern edge of it, we have this region where we have negative potential vorticity. And this is a good indicator of actually a variety of different mesoscale instabilities, including symmetric, sort of in the general case, convective and inertial instability, where you have positive, really quite positive PV. The atmosphere is stable, and so that persists across most of the map. And in the small areas, you have negative potential vorticity. It doesn't tend to last that long, which is exactly what you'd expect. We have instability that's dissipated quite rapidly. It's worth noting that the right entrance region of the jet is often a focal point of frontogenetically induced instability. So there's lots of different things going on here to look at. And so what I've done is I've taken two cross sections across this region with the aim of identifying the source of the observed gravity waves we saw at Aberystwyth. And if we look at the kind of cross section across the ridge, this A to B cross section, which goes across the UK, actually quite close to Edinburgh, in fact, we can see at first glance what appear to be inertial gravity waves propagating upwards in the lower stratosphere, so around 100 hectopascal there, kind of 12.5 kilometers. And also later on, more waves develop in this region of negative PV. This is the orography on simulation, and you can see the waters are mudded somewhat by orographic waves that appear in this orography on simulation. And now if we look at the other transect, the C to D, kind of parallel to the ridge, we can see as the jet streak moves in, this kind of high winds in association with that jet streak, we see waves again on the northern side of the jet and a few on the southern side as well. So we need to try to be careful about where these waves are coming from, and that this is the sort of challenge that we're dealing with. The first, a quick sanity check with the orography. We want to make sure that the model is actually taking out these orographic waves when we turn the orography off. This is just some islands in the Western Azores and with orography on, and you can see some really nice gravity waves there. And if we take the orography off, it almost completely gets rid of the orographic gravity wave signature, just some very small perturbations down the right. So that's really good. That means that any oscillations that we see in the orography off simulation, we can be fairly confident there's no orographic gravity waves getting in the way. And if we compare the two kind of simulations with that same transect that I said I drew earlier, we can see that they are actually very similar for this particular time step, which means that the orographic gravity waves are not playing a significant role in this particular time step, as I mentioned. In these two figures, the green stippling, which you can just about see, demonstrates where you have negative potential vorticity. And if you remember back from that idealized model simulation with the hatched region, it's sort of in a similar zone where you have the black contours, where you have your jet streak, and on the equatorward side, we have this area of negative PV, around 200 hectopascal in both the simulations. And again, we see these sort of gravity waves propagating upwards away from potentially this region of negative PV, but also the region of high vertical wind shear as well. And there's a lot going on in this diagram. We can also see one of the issues that we're having to deal with in terms of extracting gravity wave perturbations, because you have this dipole, this red-blue dipole, where you have very strong wind gradients. And so what I want to try to do is fine-tune my gravity wave filter so that all the perturbations that I see are by and large gravity waves. And that has been actually the biggest challenge, is trying to split away meteorological perturbations that are not gravity waves from gravity waves. So long story short, there's still lots of work ongoing here. And I've been doing some work based on a quite recent paper, which essentially splits the atmosphere into different regimes, looking at the kinetic energy spectrum to try to make sure that what I have is mostly gravity waves. But the aim is to obtain eventually gravity wave parameters, looking at phase speeds, momentum fluxes. And what this should do is hopefully tell us something about the source of the wave. So if you can see where the waves are coming from, you can maybe using tools like ray tracing, you can see whether the region of inertial instability is the source of the waves. So further work is going on to fine tune this filtering method. And I mentioned the ray tracing already. And the simulations with or without orography seem to be doing the right sort of thing. So another question which we want to sort of understand from this is the importance of warm conveyor belts in these extratropical cyclones in terms of generating inertial instability, because there's a lot of research that shows that that kind of process is getting worse with climate change. Warm conveyor belts are sort of intensifying essentially. So are there any implications of climate change? And there's a lot of important questions that remain about whether clear air turbulence can occur long after the initial inertial instability region has passed. And it's important not to skim over that, because that's probably one of the most important final things from the presentation, which is at the moment, what happens is aircraft are avoiding regions of inertial instability while they're there. But if the gravity waves persist in time, 72 hours, let's say, after it's initially imposed, well, the initial region of inertial instability could be long gone, and your aircraft moves through that region and it encounters the gravity waves, it encounters turbulence, and everyone's confused. Where are these waves coming? Where's this turbulence coming from? Because the inertial instability region has moved away. So that's something which is really important to look at, the time scale of the instability, the time scale of the release of the instability that we're looking at. So lots going on there. If you've got any questions, feel free to ask, and conversations afterwards as well. Thank you very much.
Thanks, Tim. Great talk and great animations as well. It was good to sort of visualize it all like that. Super. I guess a very quick question for me, just a sort of non-technical one, but I can't help but ask it, is you mentioned at the end about regimes and so forth. How have you thought about how best to communicate this with the aviation industry, and how
that's a good question.
It can be used, I guess?
Yes. So at the moment, there's a couple of standardized tools and indices that have been developed, which aircraft companies and in the industry uses to forecast clear air turbulence. So you can often, as a model output, you can sort of select your clear air turbulence predictor, and it's kind of classified. So one of the hopefully the outcomes of this is to improve that classification, and where at present the indices are too low, so it's underestimating turbulence, that can be accounted for, and it can be higher. I think also just educating pilots as well. So just because there's clear sky and it looks beautiful doesn't mean that there's not going to be turbulence. There are a lot of experienced pilots know that, of course, but education is a really important thing. Yeah, and if we can route, in terms of the flight routing, if flights can be routed around these regions, that's always the best way, to avoid. So
good job.
Yeah.
Any questions in the audience or online? Anything online? Great. Well, that is near perfect timing, so that's fantastic. So one more big thank you to all of our speakers. There's 3 excellent talks, really varied. It was a lovely evening. Thank you very much, everyone, and hope everyone has a nice evening.